This is a progress report for Andrew Ledbetter on the Ultrasonic Atomizer for Droplet Ejection. A quick review of the device consists of a piezoelectric transducer, an aluminum layer, a fluid reservoir, and a silicon chip with pyramid-shaped nozzles etched into it. The image at the right shows a 2D cut through the device, and the primary goal of the device is to eject liquid droplets, and that's achieved by generating a high pressure gradient at the nozzle tips in the fluid reservoir. So the cost function, the goal is to maximize the average pressure gradient across the nozzle tips, and that depends on several design variables. But for the scope of this project, I will only be concentrating on optimizing the cost function with respect to frequency, reservoir height, and aluminum thickness. So I'll be using ANSYS Mechanical, specifically the acoustic package, to simulate the device operation. Something that will simplify the frequency design variable is that there are 2 and sometimes 3 resonance modes within the frequency sweep between 0.5 megahertz and 2 megahertz. So this will simplify things greatly because I can look in a very small range of frequencies rather than having to sweep through many frequencies. And so these are the 3 resonance nodes. The first at the top is a half wavelength resonance. The red is a high pressure amplitude, and the blue is 0 pressure amplitude. The second photo is 1 full wavelength, and the third photo is the 3/2 wavelength. So these are the 3 resonance modes. The first resonance mode at the top occurs at the lowest frequency, and the bottom occurs at the highest. So some considerations to optimize this. It's very computationally expensive. Each simulation takes about 25 minutes. And on my lab computer, I can only run 4 simulations at a time. Unfortunately, the campus computers in the computer labs aren't powerful enough to run this simulation. So a couple options I could do, or I could consider, is using a genetic algorithm, but I don't think that there would be a very efficient way to implement that. So I'm planning to just run as many simulations as possible in the next couple weeks and generate a surface response across the largest design space that I can manage. So the work I've done so far is I've done about 20 simulations just to see how much I can increase the aluminum thickness or the reservoir height without missing too much detail with the response. So the y-axis in both plots is the nozzle tip pressure gradient, and so that's what I want to maximize. And then the x-axis on the left is the aluminum thickness, and on the right the reservoir height. So from this I can see that 1/10 of a millimeter step size works for aluminum. It looks like I'm capturing all of the details. But however, in the reservoir height, the step size is 0.05 millimeters, and it still looks like it may not be enough. So I'm going to investigate that further before I go on to generate the surface response.